Hello, everyone. Welcome to the April National Pilot Webinar. Welcome we have an exciting speaker this month. I am going to first introduce, though, our team member, May, who is our research associate, who's going to be helping me out in the future with these webinars, and I'm going to hand it over to her to introduce the speaker.
So hello and welcome to the National Newborn Screening Pilot Monthly Webinar. Just some housekeeping items. Please mute yourself while others are speaking and use the chat window to ask questions during the presentation. This call is going to be recorded and posted on the NBSTRN YouTube site. So again, welcome Dr. Christopher J. Collins. He's going to be presenting today. Afterwards, we will have some NBSTRN updates and other updates as well. We also have a poll if you want to share that for the audience members at this time before I introduce Dr. Collins.
Can you guys see the poll?
I'm not seeing it.
Okay, let me make sure. Oh, here we go. Sorry. All right, it should be up.
All right. So again, welcome Dr. Collins. Dr. Collins is the Chief Technology Officer at Key Proteo, a company developing a novel newborn screening and diagnostic test. He is responsible for strategically planning and managing Key Proteo's research and development. He received his PhD in organic chemistry at Purdue University in 2015, characterizing the performance of therapeutic drug delivery biomaterials in models of rare diseases using proteomics and metabolite quantification by mass spectrometry. After joining Seattle Children's Research Institute to work on targeted newborn screening analyses, Dr. Collins gained extensive experience in newborn screening and the development of targeted proteomic assays using dried blood spots. So today he's going to be presenting on the multiplexed liquid chromatography with tandem mass spectrometry proteomic methods for newborn screening of Wilson disease and inborn errors of immunity in Washington State. So welcome, Dr. Collins. I'm going to stop sharing my screen and you can go ahead and start sharing your presentation.
Okay, sounds great. Thank you, May, and thank you, Jennifer, for inviting me. Oh, let's see. To talk about what we're doing here and NBSTRN as well. I really appreciate it. Can everyone see the slides?
Yes.
Yep.
Oh, perfect. Okay, great. So yeah, I will talk to everyone about how we are using multiplexed LCM SMS proteomics, now measuring peptides as surrogates for proteins from dried blood spots to hopefully kind of expand the number of potentially screenable disorders in newborn screening. Specifically right now we're looking at Wilson disease, a couple inborn errors of immunity, and I'll update on the pilot study that we're running right now in Washington State. So I work for Key Proteo. Obviously they pay me and I have ownership interest in the company. So that's my financial disclosure here. So this group knows about newborn screening and how important it is, and how how effective it is at identifying these newborns that have these diseases that are need to be treated early on to be beneficial. Hopefully these kids can be identified, treated, and live normal lives after treatment. So the problem is, and what we're trying to speak to is that there are many treatable disorders that could be candidates for newborn screening, but that they lack validated methods, or they don't have specific enough biomarkers for them, or an assay that can be run in a high throughput public health setting. And we want to try and develop some new assays to expand these candidate newborn screening disorders. So using an existing technology, which is LCMS, that everyone's very familiar with, but turning from measuring small molecules to now measuring extremely low abundance cell associated peptides and proteins. So why do we want to do this? We want to help to innovate within the newborn screening space, modernize and prepare the system to bring in new disorders, hopefully through a common assay pathway. So Bill Gall and his group, they have put out this recent paper listing essential medical products for rare diseases. So diseases with treatments important enough that they say that there should be kind of protected access to them. 134 of these are listed. 61 of them are protein-related diseases without newborn screening. So can our assay speak to any of these disorders where there might be benefit to doing newborn screening? And then also looking to the future, cell and gene-based therapies are being developed, constantly. And these two papers kind of project out how many transformative cell and gene therapies might be approved, 60 within the next 10 years and maybe 10 to 20 a year. So these are all going to be, disorders that now have treatments and potentially becoming candidates for newborn screening. And so will assays be available for them when they become candidates for this system? So this is what we're trying to do: expand the number of screenable disorders using mass spec-based proteomics. So right now, MS-based population screenings are kind of limited to measuring small molecules, either abundantly accumulating in the serum because of some protein or enzymatic block, or to quantifying small molecule enzyme products to monitor an enzyme activity, right? But many disorders don't have these characteristics, so they don't have an accumulating biomarker that is specific enough that it's effectively identifies that patient group. But they are characterized by significant absence or significant reduction or an absence of proteins because of their genetic background that causes these diseases. It can knock out the protein within the cells of within circulating blood cells. Right, so not necessarily high abundant proteins in the serum, but very low abundance proteins within circulating blood cells. And so, can we develop an assay that can directly measure these proteins in these blood cells from dried blood spots using mass spec-based proteomics? So right now, there are not methods that are available kind of to do this at high throughput in a public health type setting. But this is what we're trying to develop, right? So if everyone can see my cursor, I hope. We use an internal standard, this kind of an example peptide, and the way we will tell the difference between the two population groups is if the internal standard is in blue and the endogenous kind of biomarker blood peptide is in red, it'll be at a normal elevated concentration in control, but then in the patient it's knocked out essentially. A lot of times it's absent or non-detectable. And so the normal versus the low concentration of peptide is the way we can pretty effectively differentiate between these patient groups. And we're hoping large scale to kind of enable an expansion of low abundance protein measurements within the newborn screening space, right? Similar to what small molecules did, in the 90s. So what we're developing here is a sensitive mass spec-based measurement, specifically screening for these disorders. It's very highly multiplexed and it's high throughput. So as a first proof of concept kind of application, we're looking at 4 disorders: Wilson disease, which is a copper transport disorder, and 3 inborn errors of immunity: Wiskott-Aldrich syndrome, X-linked agammaglobulinemia, and ADA deficiency. So Wilson disease is a congenital disorder of copper transport. By the time it's identified, it usually has kind of inset negative symptoms like liver cirrhosis or negative, kind of neurological damage that kind of onset and you can't undo, I guess, once treatment is started. And this is despite the fact that there's a very effective, cheap treatment that is available. So it was reported at first by Dr. Wilson in 1902, and even 100 years later, you're still seeing similar presentations in the clinic as to what Dr. Wilson was seeing then. And that is, despite the fact that there's this cheap, effective treatment that if it started early enough can, really help these kids live normal lives. The inborn errors of immunity that we're looking at, Wiskott-Aldrich syndrome or WAS, X-linked agammaglobulinemia or XLA, and ADA deficiency are kind of generally present with recurrent infections and can be deadly if untreated. Right, so they do have treatments, IVIG, bone marrow transplant, gene therapies in some cases that can potentially be curative, but are good treatments if they're identified early enough. This BBC article here describes Daniel Wheeler, who was the first British patient to receive the Wiskott-Aldrich gene therapy, even though his brother died of the same condition when he was younger, before this gene therapy was available. And Daniel's now a healthy young man So these kinds of gene therapies will be coming online. So newborn screening for Wilson's disease is not currently available. It's diagnosed through kind of a big and complex kind of clinical assessment where you look at biochemical measures like ceruloplasmin in the blood, Kaiser-Fleischer rings in the eyes, sometimes liver biopsy. Genetic sequencing is usually the gold standard kind of confirmation. Population-based diagnostics are lacking. Our CEO, Dr. Sihun Han, had actually tried to use ceruloplasmin in a pilot study for population screening of Wilson's disease, but it came with quite a high false positive and negative rate that made it kind of not viable for this application. And then with genetic sequencing, so there'd be very challenging interpretations with this. So last we checked, or last time I updated the slide, ATP7B alone had greater than 1,600 variants worldwide. And more than half of those classified as variants of unknown significance or variants of conflicting interpretation. So you can imagine a lot of cases where you get back kind of ambiguous genetic results. And then along with the other kind of things that people are working through with genetic screening for genetic sequencing for newborn screening, how are variants of uncertain significance going to be reported? Is there second tier biochemical studies that can be done to help with that, and so on. So right now, not viable for Wilson disease. Inverse errors of immunity, the screening for these, this kind of set of disorders is kind of a general measure of immune cell populations. So TREC screening for T cells and CREC screening for B cells. But because it's kind of a global measurement, it's relatively non-specific. There are a lot of primary and secondary kind of causes for this kind of lymphopenia that then kind of need to be teased out. So a more specific protein measurement screen could give a direct answer as to what these children have. And they also have the potential, the TREC and CREC screening, to miss SCID subtypes. So late delayed onset ADA can be missed, and significant percentages of Wiskott-Aldrich syndrome can also be missed. So again, direct measurement of these proteins could be helpful in these cases. So that's what we're trying to do, right? A common screening method for diseases where protein quantification would help to identify these patients. All of these diseases have protein deficits, and that's what we'll exploit to identify the patients in the study. So the diseases are listed here. The proteins that we're measuring are also listed here: ATP7B, protein for Wilson disease, Wiskott-Aldrich syndrome, protein for Wiskott-Aldrich syndrome, Bruton's tyrosine kinase, or BTK, for XLA, and ADA, obviously for ADA deficiency. And what you can see in the table is these are intracellular, cytosolic proteins, membrane associated in a few cases, and Wilson disease, ATP7B, is actually a transmembrane protein. So you can imagine this would be a very low abundance, very difficult kind of target. So that's a complicating factor. And then on top of that, we want to do it from dried blood spots, right? Where the sample volume that we get is very limited, and it's a very complex biofluid, ranging, or protein concentrations, right, are going to range from serum albumin extremely high down to very, very low. And so how do we get a sensitive enough measurement to really make this viable, right? So powerful sensitive technique is going to be necessary. So how do we do this at Proteo? So we call it our Immuno-SRM workflow. So dried blood spots get punched into extraction, or what we call the extraction plates, right? So you extract the blood from the paper along with the cells and the proteins. So then add trypsin to digest those proteins into peptides, and add an internal standard, an isotopically labeled internal standard for each of the peptides of interest. We then have specifically raised anti-peptide antibodies and bound those to magnetic beads. So the anti-peptide antibodies will bind to our biomarker peptides of interest in the extracted peptide mixture. We can then pull that out on a magnet, wash to get rid of all of the contaminating peptides that we're not looking for, elute specifically, right, our biomarker peptides of interest, and then analyze that by mass spec. A lot of advantages to this workflow. So we greatly simplify, right, the workflow, which increases our sensitivity and lets us run much faster. Concentrate the biomarker peptides from the concentration that they were in the blood now down to a much smaller volume, much more concentrated mixture. And it's very high throughput, and it's really easily multiplexed, right? So you can just keep adding more antibody beads into your workflow. The workflow stays the same, and now you're pulling out more biomarker peptides for analysis, right? So we currently have a six peptides for diseases, which I'll show you. But when we were running this at Seattle Children's, we were doing 10 to 15 plex assays very routinely. So here are our first generation targets, right? So 4 disorders, but 6 peptides, ATP7B. We have 2 peptides for that, and BTK, we have 2 peptides for this as well. For WASP and ADA, we have 1 for each. And where we have 2 peptides is just to increase our coverage of those proteins. And we went through a pretty rigorous process to select these peptides, but the main characteristic that we look for is uniqueness in the proteome, right? Is this peptide only present in this protein? So we're not going to get confounded by other proteins with this exact same sequence. And again, if you look at the way we tell the difference between the 2 populations, the internal standard in blue, red endogenous peptide, normal concentration, and Wiskott-Aldrich syndrome patient here significantly reduced. As far as background data, so we published this paper in Gastroenterology looking at a large retrospective study of 216 Wilson disease patients, 48 carriers, and 150 controls, enriching the ATP7B peptides from dry blood spots. We're plotting here our 2 ATP7B peptides, 887 and 1056, on each axis, looking at their concentrations relative to each other. You see here a normal cohort, all the concentrations that we've measured for these peptides, but then in the patients, a big shift down towards much lower concentrations. So 91 or 92% of the patients had at least 1 peptide below these cutoffs that we've set up, and they all kind of stack up along the axes, but 80% of the patients are actually within this green box. So very significantly reduced from average. If you set up a receiver operating characteristic curve, the area under that curve is 0.98, and the sensitivity, specificity, PPV and NPV are listed here. So it's very good at separating the healthy cohort from the patient cohort, but it's also really good at reducing clinical ambiguity where, if you remember, I said Wilson's disease, you kind of take in a lot of different clinical factors and then to make the diagnosis. Sometimes those things can be in conflict, right? So 32% of our cohort with genetic results, those genetic results were ambiguous. Either they had 1 variant of uncertain significance, some had 2, some had very high clinical suspicion, but only 1 variant that was found. If you look at that group and you measure their peptide concentrations, 94% of them were deficient in these ATP7B peptides. So we can add a lot of value in these cases to kind of clean up or lend support to this being a patient or not. This is also true with patients that had normal ceruloplasmin. 88% of those were deficient in ATP7B peptides. So it can provide a lot of value to these kind of ambiguous genetic cases. And this is also true for our inborn errors of immunity. If you look at our XLA peptides, BTK407 and BTK545, 97% of the patients that we looked at with BTK407 had reduced concentrations of this BTK407, and 100% of them had reduced concentrations of BTK545. All of our Wiskott-Aldrich syndrome patients that we've looked at so far, very low concentration of WASP, practically non-detectable in most cases, 100% of those. And as we looked at ADA deficiency, this is interesting because it actually depended on treatment of the patient. So we had 1 patient that was on enzyme replacement therapy that we positively identified. This is bovine ADA that they use to treat these patients. And we're not looking for the bovine ADA sequence. The human ADA sequence is distinct from that. And so the human ADA is missing. And so that's why we can say, okay, ADA is absent in this case. These other patients that we've looked at had red blood cell transfusions, and red blood cells are rich in ADA apparently. So now we measure high levels of ADA in these samples because they have had this red blood cell transfusion. So I thought that was interesting. We also were able to look at one Wiskott-Aldrich syndrome patient before and after bone marrow transplant. And before, absent WASP peptide, and after bone marrow transplant, that value had normalized. So we were able to show the change there in the reconstitution of that patient's immune system. And if you go back to these citations, there were actually other peptides that were included in this multiplex, including some general cell markers. So this truly was a larger multiplex that we were looking at here. So as we were thinking about taking our lab test that we had developed and worked so well, and what we would need to do to get it into a public health setting, the first thing that we wanted to do is kind of simplify the workflow and generate a prototype kit of all the reagents that you might need, that you will need to run the assay. And so we've done that now with a contract manufacturing organization out of California. Everything that you need to run the assay comes in the kit. You can see images of everything here. We have the antibody bead mix, all the antibodies on their beads mixed together into a single bottle. The internal standards are lyophilized into a plate. And we have dried blood spot control cards with known values of peptides from high, low, and negative. So slight modification to the workflow. You still do the punching, extraction, and digestion the same way, but now our internal standards are lyophilized into plates, enough internal standard for each assay in each well, right? The amount that one patient would need is in each well, right? So you don't have to worry about dissolving the internal standard, diluting it correctly. It's a simple pipette transfer. You then add the antibody beads from the bottle, and the rest of the workflow stays the same: wash, elute, and analyze. So we moved to this plate-based internal standard because we wanted to ensure consistency, especially because we're measuring values at the low end. That's where our patients would be. We wanted to make sure that we can give everyone the right amount of internal standard that they need every time and remove a lot of sources of error and maintain hopefully consistent averages and consistent cutoffs across time. And you can see here this works pretty well, and we've shown consistency now across plates and across kit lots. So this does work quite well. If you're looking at the linearity of using the kit, if you decrease from 100% human blood down to 0% human blood, you get a nice linear decrease in the amount of peptide that you measure. And the dried blood spot quality control cards do work as expected, decreasing from high to low to negative. Final thing we did here was to take this kit, new workflow, and subject it to a blind sample challenge, right? And this works as we expected, given the previous patient results we had. The patients are deficient in the peptides that correspond to the disease that they have, right? So the Wilson patients here are deficient in ATP7B, and ADA deficiency patients deficient in ADA. And it's still specific because within this red box here is all the other patients. So if our ADA patient is here, then this is our ATP7B XLA patients measuring higher normal levels of that non-specific peptide. So with all this in hand, we wanted to see, how robust is this? How does this perform at a large scale? What are our cutoffs? All these things that we're very curious about. So we started a pilot study in conjunction with the Newborn Screening Lab of Washington State, John Thompson and his group. It's been great collaborating with them, where we will get samples from the state, do our multiplex screen on them, targeting 50 to 75,000 newborn samples. And anything that comes in below an initial cutoff that we've set off, we will do genetic sequencing for confirmation of whether or not that actually is a patient, right? So if you look at these images, this is the state lab on their first day of punching for us. And then these are those corresponding plates being run by our technologists here at Key Proteo. So 14,500 newborns that we've analyzed to date, and I have the demographics here on these next few slides. about 1-to-1 male to female. We have a range of birth weights from less than 1,500 to greater than 3,500, kind of larger numbers at larger body weights. And we also receive date of collection after birth. So from we've had less than 24 hours and then to more than 6 days. Usually we get them within the first 3 days, or they're collected within the first 3 days of birth and then sent to us. Here's our demographics. So it's a predominantly white set of samples that we've received, but with significant numbers of Hispanic, Asian, Black, and Native American samples from state. So all those, so 14,534 newborn samples that we've successfully analyzed. These are the concentrations of all of our peptides in these samples, right? So ATB7B, our 2 Wilson disease peptides here. You can see the averages. Wiskott-Aldrich syndrome is here, ADA deficiency, and BTK then is our 2 XLA peptides, right? So going very well, quite robust, and we're just continuing to churn through these samples and collect data. In this table down here is our averages and our current tentative cutoffs. These will obviously change, as we run, another 15,000 samples. So it's a work in progress, but this is what we're working with right now. If we break it out by gender, we have not seen statistically significant differences between the two, between male and female birth genders. We're interested to see this because 2 of these diseases are X-linked, so we weren't sure if there'd be any difference between those 2 cohorts, but right now it looks like there is not. Body weight, our Wilson disease peptides and our XLA peptides don't seem to be affected by body weight at birth, but Wiskott-Aldrich syndrome peptide and our ADA peptides seem like they might be slightly lower in these very light, less than 1,500 gram newborns, but nothing that's been below our current cutoffs so far. So no false negatives because of, false positives because of this difference with Wiskott-Aldrich syndrome and ADA in body weight. And then here as well, no real differences that we've noticed as you look across the ethnicities of the samples that we've had for any of the peptides. So far, looks like average is very similar. So what samples have we sent for sequencing so far? We have 2 kind of case studies that we'll talk about, that I'll talk about here. We have sent 1 Wiskott-Aldrich syndrome patient that was sequenced because it came back below an initial cutoff. But what we got back from PerkinElmer Genomics, who's doing our sequencing, is that there was insufficient DNA there to do the sequencing. And then when we went back and looked at the concentrations of all the peptides, we also saw that this patient also had produced concentrations of BTK peptides, right? So those XLA peptides that we look at. So we're suspicious for, okay, is this just kind of a general lymphopenia, and that's why there was not enough DNA there to do the sequencing. And so we've incorporated this into our review. If we see we will incorporate this into our review. If we see a Wiskott-Aldrich syndrome peptide that is reduced, we'll also look at the WASP-BTK ratio and kind of use those together. So currently we are, right, because if the XLA peptides are normal and high and the WASP is greatly reduced, that ratio should be very low. So that's what we're looking for. The Wiskott-Aldrich syndrome patients now will be flagged if that peptide is below our cutoff, and based on the patient samples that we've run, the WASP-BTK ratios are within that patient range, so less than 20% of BTK. So we'll have 2 things that we look at here. Everything else we'll look at flagging if the peptide concentrations are below the cutoffs, which we've set up as a percentage of the median of the sample cohort at the time. 0 samples have been below these concentrations for ADA and XLA, so we've sent nothing for sequencing there. but we have sent one for Wilson's, and this was just below, at our cutoff, basically. If these are our cutoffs here in the table, for ATP7B887, cutoff is, let's say 76, and the concentration in this patient or in this sample was 74 for that peptide. For ATP7B1056, the cutoff is 58, and this value was 57. So both values below the cutoff, right? And so we sent it for sequencing, although very, very close. And what we got back was actually two variants, one pathogenic and one that actually came back to us from PerkinElmer as a variant of unknown significance. This variant 2, this synonymous variant, based on this paper that they cited showing some possible in-frame exon skipping, but no physical evidence. And we were unsure about this, especially because if you look at the allele frequency, minor allele frequency of this variant here, 2.5% of the population, that seems quite high. So we're calling this a likely carrier, although it was reported to us as a variant of uncertain significance. But we think one false positive in 15,000 samples for diseases is reasonable performance, and shows that it's working. We had this low sample and we found two variants. We've also sampled some Wilson disease patients in what we're calling a gray zone above the cutoff to look for any carriers or any false negatives. And what we found so far in running some of those samples is listed here in this table. So I'm listing 4 here, the values of ATP7B887 and ATP7B1056. And we have found some carriers and one healthy individual. And this synonymous variant has actually cropped up 3 times now. So that kind of goes along with, okay, this variant is quite common. So that's an update on the pilot study and our technology. What are we thinking about for the future? As I alluded to, we think that there are a lot of other diseases that we could potentially put into this multiplex. We have 2nd generation targets in mind that we're going to be looking at. So continued R&D on those. The nice thing about this is that if new peptides get added to the multiplex, the workflow, both in manufacturing and, well, I'll say the workflow doesn't really change for the user of the test, right? The assay is going to be functioning exactly the same way. There'll just be more antibodies in the antibody mix, and the manufacturing only has to change very slightly to incorporate new antibodies. So we think it'll be kind of interchangeable and modular in that way if we can get going. So we're excited about that. If anyone has any ideas for targets that might be good for us to look at, I'm happy to hear it and to talk for sure. We also think there are plenty of applications here for 2nd tier testing using protein quantification, peptide quantification here. We actually have reported with our collaborator Tong Zhang as the lead author, a 2nd tier test for LSDs, MPS I, and Pompe disease. If you want to look up this citation, showing that we can identify the very severe cases of these because they're absent in protein, where more mild cases are not. So we think there's a lot of potential application there, and then other clinical and diagnostic application of protein measurements from dried blood spots as well. So I'll acknowledge our CEO, Dr. Si-Hoon Han, our Director of Business Development, Sean Sandin, our technologist, Claire Klippel, all of our collaborators that have been helping us with this, everyone at the State Lab who have been super helpful and great to work with. And I'm happy to answer, and obviously everyone who joined the call, and the STRN for having me. And I'm happy to answer any questions that have come up during the talk. So thank you.
Thank you, Dr. Collins. It was a great presentation. So if you guys have any questions, you feel free to raise your hand. I can call on you and can unmute yourself. I see May Baker has her hand up. And you can also write your question in the chat as well. And me and May Leach will tackle them together. Go ahead, May Baker.
Okay, hi.
Hi, May.
Wonderful.
How are you?
Yeah, I'm good.
Thank you.
Wonderful presentations and very nice to see you making progress. Actually, I have a solo question, but I want to respect my colleagues. I'm going to ask one, then when I have a chance, I will ask. The first one I want to ask you is, I noticed a couple of conditions that use 2 peptides. I want to ask what's the rationale in terms of instead of 1, if it's a signature, why you need 2? Could you explain the reason?
Yeah, so it's a couple things that go into that. Ideally, we would, so part of it is it's hard to develop these antibodies. Sometimes only 1 antibody hits. And that's the antibody that you have for 1 peptide, right? We usually start out trying to develop at least 2 or 3. And then if we can add those into the multiplex, that works well. For a couple of other cases, so for like BTK, we found that in one, so first we had BTK 407, we found that there was a common, or not common, but there was a mutation that was causing a false negative. And so we could develop another peptide that kind of hit that region and use them together. So you can kind of rationally say, oh, these are very common mutations, or these are causing false negatives in those cases where we can find them. Then we can develop other peptides for the multiplex there as well. So a couple of reasons, mostly just to give us more coverage, because we've seen some cases where, one will be significant, like reduced more than the other, and it's always better to get a more global look of the protein itself, right? So that's kind of our rationale.
Thank you.
Yeah, thank you.
I'm not currently seeing any questions in the chat, May, so if you want to ask another question, May Baker, go for it.
Okay, my second question is, I just want to verify for Wilson disease, when you describe the patient population and normal population, I do see overlap. Is that true?
In the peptide concentrations?
Yeah.
Yeah, so there are, in that paper, we describe, so 92% of the patients are reduced. And so there are some false negatives that we found in that cohort from that paper. But what we found is that those are arising from a couple of common mutations that are, that for some reason, a protein is produced in kind of a normal amount, but I guess, is like non-functional, right? So those are rare mutations, and we've identified them. So if they come up, we can have been thinking about, okay, can we design peptides for these? But yeah, in that cohort, there were a couple of specific mutations that caused false negatives.
I just will be sure I understand correctly. Thank you.
Yeah, sure.
Joseph Hill, you have your hand raised?
Hey, I guess just to follow up before my question, I assume there's similar possibilities for false negatives with Pompe and MPS1 with mutations that cause enzymes that are present but not active. But
sure,
yeah,
it's possible. Yeah, and if you the thing about, so check out that paper, because what we found is that when we were measuring those peptide protein concentrations, the severe cases were all completely absent, and the less severe cases were just reduced. So you could discriminate between those two populations, but yeah, I think, until we look at every mutation, we're never going to get away from the possibility that there's a mutation out there that we don't know about that,
because every protein is going to be unique in its own different way. Right. But my actual question, you mentioned like 5 or 6 different multiplex disorders that you've worked on so far, but you also said some pilot at a hospital, you had up to 14 plex or something. Have you guys looked into measuring IRT or TSH with this method and multiplexing that in?
We have not, but yeah, not a bad idea. We can look into it, but we haven't. In our immunology manuscripts, we report a couple of additional conditions, and then we also have a T cell marker, NK cell marker, platelet marker as well. But those two we haven't looked at.
Thank you.
Since you have been this, along with the questions that have been asked, Dr. Collins, can you speak a little bit more about the scalability? Because I know you said you were looking for other conditions that you want to use this method, a proteomics approach to be used for. So could you speak to like the scalability as far as developing it for other conditions, a proteomics approach, as well as the since you're using it in the state program, you also talk a little bit about how practical it was to implement in the state program.
Yeah. So scalability in terms of the number of conditions we could potentially look at? Or?
I'm assuming that it takes you quite a significant development as far as the
antibodies.
Yes, the antibodies to actually for the peptide.
Right. Yeah, that's true. Those take some time and effort to develop. Yeah, absolutely. But you know, we think we've been through the process a bunch of times now, and I'm not going to say it doesn't take time, and I'm not going to say it always works, because antibody development is a little bit of a, you know, art sometimes. It's just like that rabbit that you injected your peptide into, what's its immune system doing on that, you know, comes down to a lot of specific things. But we can do things there that give us like more shots on goal to try and have an antibody that is successful. So I think, you know, it does take time for sure to go from this is a target that we want to look at to validated antibody to validated assay. But we have pretty well developed workflows for that. And we, you know, people have reported similar kinds of assays in clinical diagnostics where they're looking at 50 or 70 or 100 different peptides in their multiplex. So I do think it's very highly scalable, you know, given that we can take the time to develop the antibody. I'm not going to say that that's easy. So as far as implementation in the public health lab, so I wasn't meaning to say that Washington State was running this themselves. They're collecting samples for us and sending it to us here, and we're running the samples internally. So, you know, we would love to set up some kind of pilot like that. You know, if anyone has the bandwidth, you know, we've gotten our workflows here down, you know, to where it works really well, and the instrumentation is pretty robust. And, you know, inject to inject times are short. And so we think it's high throughput. It's something that's doable if someone has the bandwidth. But as far as what it's going to take to actually implement this in a public health lab, we're still going to have to find out once we have a partner who wants to work with us on that, right?
Jennifer, I have a question.
Sure, go ahead, Bob.
Hi, this was a terrific presentation. Thanks very much. I heard you say rabbit, and I was surprised because I thought you would be looking for monoclonal antibodies as your binders. Have you looked at or compared polyclonal with monoclonal antibody preparations?
So we do have monoclonal antibodies. they get a specific antibody within the polyclonal set is selected and then produced at a higher scale by our antibody production partner. So we do have monoclonal antibodies and the DNA, or plasmid DNA for those, so we can reproduce them readily.
Well, that's great. That's very promising.
It looks like we have a question in the chat from Joe. He asked, can the mass specs currently used in newborn screening programs be used for this assay?
So we do use a more sensitive instrument for this because the peptides are in such low concentration. So I guess we haven't tested specifically, whatever different instruments that all the newborn screening labs have around the country. But my suspicion is that a more sensitive instrument is going to be needed. So we're working with instrument manufacturers on that to try and partner with them to make it easier. But it's a good question because it's an important point. But yeah, so we use a Xevo TQ-XS, which is a slightly more sensitive instrument.
So may I jump in the some topic, make additional comments? Actually, I was going to ask some question like Drew did. The comments I want to make is because of the technology and Chris was emphasized very, very low abundant protein. So you need this antibody to enrich that. So I think the some technology really you can apply to not so, low concentrated ones. And in that process, you don't even need the antibody enrich. So this is one thing that simplifies. Secondly is to answer Joe's question is the kind of mass spec we have now, yes, you can use it. Because I said that because we did some project. So because it's abundant, we don't need to use antibody. And the same process, you do the trypsin gene, digest that, you find the signature. So I think it's durable. That's what I want to say. And also I want to emphasize, as Joe was said, it's why in our process, we very, very carefully, because the genetic variants and will have a protein consequence, amino acid change. And when you select the peptides, it's very important that you really do your homework, knowing that region is any other changes could potentially. So that is a very, a lot of informatics have to go front to whatever you're interested in peptides. And, I think logical I want to say is you have a DNA structure change. Of course, you have your translation, when you do the protein, the change, then if you really trying to find the signature, then, just need to be careful. So it's why I want to emphasize what Joe said, every single variant could have a consequence of your peptides.
Sure. Yeah, no, that's true. We definitely do a lot of upfront work to make sure we're selecting the right peptides before we even go into the antibody production, right? So it's extremely important. But the vast majority of the variants that we've been able to look at so far have had significant protein concentration impacts. But yeah, like we've been saying, there's no way we're going to get around some of these rare variants that don't have that. We can find them, we can develop for it, but that's a continuing effort. And yeah, as far as mass spec, it's going to depend on the target for sure, as May had said. So higher abundance not going to be as much of an issue.
I think you're muted.
Sorry about that. I hope you guys can see my screen. I was going to hand it over to Dr. Chen to make some announcements on the MBS trend side. Everybody can see my screen?
Hi, everyone. Thank you, Dr. Collins, for a wonderful presentation and all the great questions that the participants asked today. And I'd like to just end today's presentation with some updates from MBS Trends. So definitely check out our podcast, Newborn Screening Spotlight. And our latest episode is with Dr. Stephen Kingsmore, who's the CEO and president of Rady Children's Institute for Genomic Medicine in San Diego, California. In this podcast, you will hear about his purpose and to improve the lives of newborns to prevent avoidable and unnecessary death due to late diagnosis of rare genetic conditions. But also in this podcast, he really opens up about the challenges in making this dream a reality. And it's a really personal journey that he shares on this podcast. So definitely take a look and listen and subscribe and share this podcast with your colleagues. Next. And save the date that we have our exciting network meeting coming up in May 18th and 19th. Save the date, block it in your calendar right now if you guys can, from 12 to 4 Eastern time. It's going to be on Zoom. So once you register on this link, it'll take you to a registration site. And as it gets closer to the network meeting, we'll send out the Zoom link to everyone. And it is free for anyone to attend. So definitely share this link, tell your colleagues. And this will be focused on celebrating the 15 years of collaboration and innovation in newborn screening research, celebrating 15 years of MBS Trend, and also the 60th anniversary of newborn screening. So we're going to have a great bunch of speakers. Tentatively, the agenda will be that day one, we have tentative, this is a tentative agenda, but we'll have a focus on advocacy, the role of advocacy. And in day two, we'll have key stakeholders from different institutions sharing their the history and the current and the future of newborn screening. So just gonna give you a little teaser and register for this for this network meeting. Next. Also, love to share about this new funding opportunity that was shared by our program officer at NICHD. That NHGRI has this new funding opportunity, which is entry-level modules for training for genomic research workforces in R25 clinical trial not allowed. And they have a pre-application webinar, so we definitely want to make sure you know about that. It is on Tuesday next week, April 11th. Definitely register for it. So if you just search on the NICHGRI website, you'll find this and also about the announcement. But the application is coming up. It's in June 1st, 2023. So definitely, if you're interested, check this out. And the idea is to encourage paraprofessionals and early entry workforce to get into genomic research. So there will be support for that. Next. And next month, I'm really excited to be one of the speakers. And in this presentation, I will highlight the introduction of modeling and newborn screening pilots and really introduce how computational models can help inform the design execution of use of newborn screening pilots. And in this presentation, we'll focus on some use cases, the application of these models for SCID, Duchenne, infantile versus late onset Pompe disease, and the Rest nomination. This presentation stems from the 2 papers that was published in the Frontier in Genetics. So we'll also send some links to those 2 papers if you want to take a read before you listen to this presentation, so you can bring with some questions. And follow us on social media. We're on YouTube, Twitter, Instagram, and Facebook. So definitely follow us there. Thanks. Oh, actually, the May is on Tuesday. I want to make a correction. It's the first Thursday, but for that first Monday, we have the advisory board meeting. So be sure to register for May 2nd. I like to correct. I'll make that correction that I'm actually giving that talk on May 2nd, not on the Thursday of May 4th.
Yeah, we have the ACHDNC meeting. I know is the 4th and the 5th. So
and that's all I have.
Yeah, thanks, Key. Yeah, we changed it to the Tuesday.
Jeff, are you mute? I can't hear you.
Can you guys hear me?
Yeah, the rest of us can hear you fine.
Oh, okay. I'm sorry about that. Yeah, unfortunately, fortunately, the ACHD meeting is on that Thursday and Friday, so we moved it up to the Tuesday. But thanks again, everybody, for joining this month's call. Again, we hope to see you next month on that Tuesday, May 2nd. So thanks again, and we'll see you next month.